All right, I'm going to be working on 7.2, starting with number 1. So number 1 for 7.2. Find the volume of the solid obtained by rotating the region bounded by the given curves about the specified line. Sketch the region, the solid, typical disc or washer. So we start with y equals 2 minus 1/2 x. The other equation, y equals 0, x equals 1, x equals 2. And we're going to rotate this about the x-axis. All right, here we go. First thing is to draw a picture. So, all right, let's get a couple of things here. Y equals 0, let's take care of that. Y equals 0 is the x-axis. X equals 1 is this vertical line. X equals 2 is this vertical line. So that's these. And then the actual other equation is a line. So this is a line, we could write that negative 1/2 x plus 2, and it has a y-intercept of 2, so I go up 2. And then I go, slope is down 1 to the right 1, so down 1 to the right 2, down 1 to the right 2. So I get this line here. I'll draw it in blue. All right, so we want to take the region bounded by all those curves, which would be this region right in here. All right. And we want to, well, I should point out that the reason why it's not this region, even though it looks like it is, because that y-axis doesn't stop it, it keeps going. And in this region, it is bounded by 3 of the curves, but not all 4. So this one is bounded by all 4 of the curves. So this line, that line, and this line. So that's the region. We want to take that region and rotate it around the x-axis. So we're rotating around the x-axis like this. So if I take an arbitrary rectangle in here like that, come out over here on the side like I did in class, draw your x-axis, draw your rectangle, and then determine your outer radius, which is the distance from the axis of rotation to the outer edge of the rectangle. So this distance right here, that distance right there is just the blue line, because the distance from the x-axis to the blue line. So that distance is 2 minus 1/2 x. And then the inner radius, which is the distance from the x-axis to the bottom of the rectangle, is actually 0. Right? Because it's on the x-axis. As we move that rectangle over, that bottom edge always touches the x-axis. So the outer radius is this, the inner radius is this. We take that, we rotate it. When we rotate that around, we get this, our axis of rotation here. And so we get a disk, basically. But we're still going to use the same formula from class. So the formula is pi times integral a to b, the outer radius squared minus the inner radius squared d whatever, in this case dx. So we'll want to set up, for us, a to b is where we start and stop for x, so it's going to be pi integral 1 to 2 of the outer radius, which we said was 2 minus 1/2 x, that quantity squared, minus the inner radius, which is the bottom of the rectangle, which was always 0, so that's really not going to even factor in dx. So this is pi integral 1 to 2. This is gone. I'm going to square this for, what is that, half minus x. Let me see, I'm going to make sure I get 2 1/2, yeah, minus Wait, minus 2x minus 1/4 or plus 1/4 x squared, and then dx. So when you multiply this times itself, just double check it. I'm feeling real unsure about this. I don't know why. Sometimes that happens. 4, that's -1, and then -1x, so it's -2x, and then the last one, yes. Okay, so that's it. And then you integrate. Just remember your pi out here. Integrate, you get 4x minus x squared. Let's see, plus 1/12 x cubed, evaluating 1 to 2. Oh. Evaluate 1 to 2. So you plug in 2, figure out what you get, plug in 1, figure out what you get. Just remember the pi is going to be out in front of everything. So that would be the area of that thing rotated around now. What would that region look like if we rotated it around? You know, you've got this thing rotate around the x-axis, probably something like that, some solid. And what this represents is the volume of that solid. Sorry, what that represents is the volume. All right, let's look at number 3. For number 3, we have x equals 2 root y, x equals 0, y equals 9, and you want to rotate this about the y-axis. So picture time. Hold on. There's y right there. Picture time. X is square root 2 square root of y. So if y is 0, x is 0. If y is 1, x is 2. Right? If y is 1, x is 2. What if y is 4? 2, 3, 4. If y is 4, square root of 4 is 2. 2 times 2 is 4, so x is 4. So what was that? 2, 3, 4. So x is 4, so like that. So it looks like this. This is x equals 2 root y. And then if x is 0 is the next one, x is 0 is the y-axis, so we've got this. And y is 9. Oh crap, that's off my graph. It's up there somewhere. 9, and it goes across like that. Like this. Okay. So I can see the region pretty clearly. It's this region in here. I want to rotate that around the y-axis this time. The y-axis is this. So what we can do now is draw a rectangle, and this time we're going to use a horizontal rectangle like this. And I'll draw it down here below, that rectangle like that. I'll draw my y-axis, which is here. That's my rotation axis. And then I'll ask myself, what's the distance, the outer radius, and then what's the inner radius? Well, the inner radius is simple. That's going to be 0. The outer radius is distance from the y-axis to this edge. This edge is that black curve. So it's this right here. It's 2 root y. And that should be what I need as far as the right function and left function. So it's 2 root y and 0. But I also need to figure out my limits of integration. So I'm going to go from 0 to 9, and that you can tell by the picture. And then we just set it up in the formula. So our formula is going to be pi integral a to b. It doesn't matter. That can be c to d. Outer radius squared minus inner radius squared d whatever, in this case it'll be dy because our rectangle is horizontal. So it's pi integral 1 to 9, and then outer radius, which is this, 2 root y squared minus the inner radius, which is 0 squared, which won't matter. So we get pi integral 1 to 9. When we square this, we get 4y, 0's gone, dy. This is actually pi times 2y squared. Why did I put 1? This should have been 0. Oops. 0 to 9, sorry. 0 to 9. I was looking at the 1. And then just plug in, so that's pretty simple from there.
What?
Your drink?
Yeah.
I know. What's going on?
Trying to be over there.
Have you tried it?
Yeah.
Okay. I just finished the video for it. I know, me too. It's been quiet this morning. It might be the weather. You like this? Yeah, me too. I can't wait for it to rain this weekend. I guess that's what they keep saying. Let's see. I've got 11 minutes.
It's nice when it rains.
It's what?
It's nice when it rains.
Yeah. You have specific questions?
Not at the moment.
Okay. Would you mind if I talk in the background?
Just sort of work.
Yeah.
Hi, camera.
All right, so we're going to do those curves rotated around the x-axis. So we've got to draw our picture first. Y equals x cubed. This one. It's like this. Y equals x will look like this. I need to adjust that. Oops. My y equals x cubed isn't good enough.
Which one are you doing?
7.2?
Okay.
Yeah, I did 7.1 already.
Do you want to picture of 7.1?
Oh yeah, go ahead.
Thank you.
No problem. So this is y equals x cubed. I had to kind of flatten it out a little bit because y equals x is above it like this. Goes like that. Okay. It's y equals x. And then x greater than 0 means we're just looking this way. And I think the region is pretty obvious right here. Right in there. So I think I'll blow this picture up so I can exaggerate it a little bit. You've got the x cubed coming in here like this. You've got y equals x like this. And that's our region. And we're rotating around the x-axis, so around this axis. Here, this axis like this. All right, so we're going to use a vertical rectangle right here. We're going to imagine we're going to transpose that out here. Here's the axis of rotation right here. And so I need to figure out what the outer and inner radius of these things are. So the outer one is this, and the inner one is this one right here, like that. So the distance from here to here should be the red function, which is just x. The distance from here to here should be the blue function's height, which is x cubed. So this is my outer radius, this is my inner radius. And now I just go to the formula. Oh, I also need to figure out where they hit each other. I didn't mention that. I should have mentioned that. If you set those two equal to each other, x cubed equals x. Bring the x over. factor out an x, you actually get three solutions, 0, 1, and -1. So they hit each other here at 1 and at -1 down here, but you're not looking over here. So 0 to 1 is the integral. So we're going to go pi, don't forget the pi, 0 to 1, outer radius squared, so x squared minus inner radius, x cubed squared dx. And then you can square that and integrate that. That's all I'm going to do. I'm not going to go any further. You just let me know if you have a question, okay? You can interrupt me is what I'm saying.
I'll wait politely until you're.
No, seriously, don't wait. Just because these, might take a little while. Number 7. We're going to take y squared equals x, and x equals 2y, and we're going to rotate this about the y-axis.
So did you want us to boil it down to a numerical answer?
Don't interrupt me, please.
Well, you know what, you just said something otherwise, so bite me.
What do I want to what? Boil it down?
Yeah, I think.
Yeah, you should. You should practice getting to the numerical answer.
Okay.
I won't do it in class. I won't do it on the homework solutions because it's just
It takes a while.
it's just taking a while. But you should practice it because that's just, arithmetic, and it's tedious, but it's not hard. Use your calculator. Check. You can check the answers in the back because I think they're odd problems, right?
Mm-hmm. I'm gonna do the even ones afterwards.
Yeah, I want to go back and do the evens on video. I don't know if I'll have time.
Well, you got everybody to take that down.
You got what?
For the text messages that, yeah.
Mhm.
I'm really starting to get that now. I'll stay with Alan.
Yes. That works. All right. These are looking like functions of y because they're both solved for x. I'm rotating around the y-axis. Let's see. I'll write this backwards. If y is 0, we've got x is 0. If y is 1, we've got x is 1. So this is our parabola opening up sideways like this. This is x is y squared. And then x equals 2y. If y is 0, we get 0. So we're here. If y is 1, x is 2. And so we're going to have something like this. Oh, that's supposed to be a straight line. All right, so I think I can see the region here. The region bounded by these is in here. I'm going to want to use horizontal rectangle because I'm going around the y-axis, and these are both functions of y, so I'm going with something like that. All right, so let me try and do this without having to redraw it. It's kind of small, but all right, so I'm going to do my rectangle up here. Just transpose that thing up here. Do my axis of rotation here. And I need to find the distance from here to here. That's my outer radius, that's my inner radius. The outer radius is the distance from the axis of rotation to this edge, which is the blue. That's the blue curve right there. The black curve is this one right here. So the blue one is 2y. And I'm sorry, I'm being distracted here. It's very hard to concentrate right now. So y squared is the inner one. Come on. Come on.
Well, hey,
Take
I gotta
it,
be
take it, take it.
Okay, thank you.
All right, so the inner one is this one, outer one is this one. Go to the formula. Oh, we need to know where they hit each other. And we're doing things in terms of y, so I can tell it's at 0. I need to figure out where they hit each other up here. So intersection, I'll set the two equal to each other. Where's y squared equal to 2y? Well, that's where y squared is minus 2y is equal to 0. Don't divide both sides by y. That's a big mistake. Factor out a y. You get y is 0 and y is 2. So see, if you divide both sides by y here, you get y equals 2. That gets one answer, but doesn't get them both. There's actually two of them. So just an algebraic thing, be careful there. So we know that this value up here is 2. All right, integral time, pi, because we're doing a volume. 0 to 2. Outer radius is 2y squared minus inner radius y squared squared dy, and then you work it out.
Can you do it again?
I will, but x root x y equals 1. I got it. X root x y equals 1. I'm good. Did you take a picture? Number 9. All right, so this is the first problem that I'm doing here in the homework where our axis of rotation is not one of the coordinate axes. It's actually just an arbitrary line. So we've got to make sure we get our picture right. All right, so y equals x is the diagonal. Y equals the square root of x. Looks like this. They hit each other at 1 because the square root of 1 is 1. And it actually goes above like that. And so I can see my region. However, my axis of rotation is not the x-axis, it's y equals 1. Y equals 1 is actually this line right here. So I want to take that region and rotate this region about the line y equals 1. So my rectangle in here looks like this. It's a vertical, because these are both functions of x. I'll come out here, I'll draw my axis of rotation. I see my rectangle looks like it's about right here. I've got the blue function here. I've got the red function here. And you know what? I'm going to draw this a little bit bigger. I'm not happy with this. I'm going to blow this up. I'm going to zoom in on it. Okay. Y equals x was here. That. So this one was root x. This one was x. Our rectangle's here. Our axis of rotation is there. So when I draw my axis of rotation out here, my rectangle right here, I have the red curve here, blue curve here. And so what I need to do is be really careful and imagine I'm standing on the axis of rotation looking out towards the rectangle. I'm looking for the edge furthest away from me. That's the outer radius. So I need to know what the distance is from here to here. And then the inner radius is this distance. But I'm way up here at y equals 1. The x-axis is actually here. So if I want to know this distance from here to here, I can tell you the distance from here to here is the height of the red function, which is just x. So I know from here to here is x. I know from here to here is 1, so this must be 1 minus x. I should do that. Yeah, that's fine. So if this distance is 1 and this distance is x, then this distance from here to here is 1 minus x. Using that same logic, I know that the distance from the x-axis down here up to that top edge of the rectangle is going to be root x. The distance from here all the way to here is 1, so this is 1 minus root x. And so my outer radius is this, and my inner radius is this. And so I go to my formula. Do I know where I'm integrating from? Yeah, I'm going from 0 all the way to an x value of 1. So pi, integral 0 to 1, outer radius, which is 1 minus x, that quantity squared, minus the inner radius, which is 1 minus root x, that quantity squared, dx. And I would FOIL these out and FOIL that out and get it all together and collect like terms and do your integration and be done. It's exciting. All right, picking up on section 7.2. Got somewhere, I think we're around number 13. So number 13. So the region enclosed by the given curves is rotated about the specified line. Find the volume of the resulting solid. So y equals 1 over x. X is 1. X is 2. Y is 0. So that's our region, and we're doing this about the x-axis. All right, so let's go ahead and start with our drawing. So let me take care of the easy things first. I've got a lot of colored markers here today. So let's try x equals 1. It's going to be here. So x is 1. We've got x is 2. It's over here. I've got y is 0. Let's see, that looks like the other one. Oh well. Y equals 0 is the x-axis. And then we have y equals 1 over x. So at 1, the value of that function is 1. At 2, the value of the function is 1/2. And we know that the function looks like this, goes up, goes like that. So I think it's pretty obvious what the region is. We've got this region right in here. And we want to rotate that around the x-axis, which is going to be this axis right here. Well, we're rotating around the x-axis. And I'm going to kind of clean up this side a little bit because I'm going to transpose that rectangle that I'm about to put in there. So we're going to go around the x-axis. We're going to use a method of discs or washers for this. Then my rectangle that I draw is going to be perpendicular to the axis of rotation, noticing that the blue function is always the top edge of the rectangle. The bottom edge of the rectangle is always going to be the x-axis, or y equals 0. So now bringing that over here, we have the blue function on top. We have y equals 0 is the bottom. Our axis of rotation was also here. So what we need to do is determine the outer and inner functions or distances So the outer distance is the distance from the axis of rotation to the edge furthest away. That's just the height of that function, that's 1 over x. And then the distance to the inner edge right here is always 0. So that's all we need to set it up. The integrand, now the limits of integration are from 1 to 2, because that's the variation we have there on x. So the setup of this integral is the volume will be pi integral from 1 to 2 of the outer function squared minus the inner function squared dx. So the outer function is, I didn't label this, this is the outer function. This is the inner function. So the outer function, 1 over x squared, and then 0. So this is equal to pi integral 1 to 2. When you square that, you get 1 over x squared. 0's gone, dx, and then the rest of it's pretty clean. All right, moving along. Let's take a look at number 15. I'm waiting for one of these to get hard. Let's see. Okay, we have for 15, it's x minus y equals 1, y equals x squared minus 4x plus 3, and we're rotating this about y equals 3. All right, so this one looks a little more interesting. So here's my picture. Let's start out with the first one here. I'll do it in red. This one. If I solve this for y, get y equals x minus 1. And that way it's a function of x. And if I graph that, that's a line. It has a y-intercept of negative 1. Has a slope of 1. So it's going to start here, up 1 over 1, draw a straight line. That is y equals x minus 1. The next function I have is a quadratic function. It's a parabola. And so it might be worthwhile if I know how to graph a parabola function. The most important part of this is to understand this is a parabola that opens up, so you know it looks like this. It would be nice if we know the vertex. Vertex, very easy to find. You remember that on a parabola, the slope of the tangent line at the vertex is 0. So if we just take a quick derivative of this, we get y prime equals 2x minus 4. And that's the slope of the tangent line. I want to know where that's 0. So if I set that equal to 0, you get x is 2. So if I go over here to my graph at x equals 2, well, actually I need to find out what the y coordinate is. So let's take that 2 and plug it in here. If we plug in 2, we get 4 minus 4 times 2 is 8 plus 3. So we get negative 4 plus 3 is negative 1. So the vertex, this point right here, is x coordinate 2, y coordinate negative 1. So if I go out to 2, I go down negative 1, I'm right here. And then it should open up. Now I don't need to, but I could also find the x-intercepts to get a better graph. So I could just take the original function, set it equal to 0. So if I factor this out, x minus 3, x minus 1, set that equal to 0, you get 2 solutions, 3 and 1. So I know I have an x-intercept here, and I know I have an x-intercept here. So when I go to draw this, it goes like this, and over here it goes like this. And you can see that I am going to hit that other line somewhere over here. Right there, and I'm going to have to figure out where that is, but I'll do that in a minute. All right, so there, I think we see the region. I hope you see the region that's bounded by those 2 functions. It's right here. And we're rotating this about the line y equals 3. Now y equals 3 is a horizontal line and it's moved up 3. So, 1, 2, 3 up here. So I'm rotating around that line. So that region's going to go around this line and we're going to get some solid. I'm going to use vertical rectangles. So here's an arbitrary rectangle. And I just want to verify that as I move this left and right, that the function on top stays the same, which it does, it's the red one. The function on the bottom as I move from left to right is always the blue curve. So the vertical rectangle will work for me. So now what I'll do is I'll determine, I'll transpose things over here. So here's my axis of rotation. Here's my x-axis. My rectangle's in here. I have my blue curve, which is always on the bottom. I have my red curve, which is a line, on the top. And so now I just need to figure out these distances. So I'm rotating around here. All right, so what is the distance from this line all the way down to the outside edge of the rectangle? And then what is the distance from here to the inside edge? So let's talk about the outside first. All right, so the distance from here to here is 3, right? So if I look just here to here, that distance, let me do it in a different color. This one's a little tricky. Distance from here to here is always 3. And then we need to tack on this much. So how much are we gonna actually add on to this? Well, if you think about plugging in the number 2, right? If you plug in the number 2, it's going to spit out -1. So if you plug in 2, it spits out -1. If we were to take 3, we want this distance to actually, like if this rectangle was right here, we would want this distance right here to be 1. So we have 3. If we plug in 2, we get -1. We don't want it to be -1. We actually want it to be +1 because it's a distance. So what we're going to do, this distance right here to here, this is the function. What was the function? It was the parabola x squared minus 4x plus 3. So that's this distance. But you have to be extremely careful here because I don't want to just add it. If I take 3 and I add the function's value, I'm going to add -1, and then that's going to mean that it's actually 2, which it's not. 2 would be up here. So I need to actually subtract this from this to get the signs to switch. I know that's a confusing idea, but it's part of what makes this a little challenging, is you're looking at a distance as opposed to just the function's value. So this distance here should be 3, and then instead of plus this, minus this. Okay, so let me explain again why this is working this way. If I were to go to 2, right, just as an example, then the distance from the axis of rotation up here all the way down to the bottom, okay, so from here all the way down to the bottom would be the 3 that I need to get from here to here, and then the distance from here to here. So if I plug that 2 in to this, you get 4 minus 8 plus 3, that's -1. So if I were to just add this, if I were to do 3 plus this, it would really be 3 minus 1, which I don't want because I want it to be bigger than 3. So I have to subtract that. So it's going to be 3 minus -1, which would be 3 plus 1, which would be 4. And that's what the rectangle would be right here. And then as you move from left to right, because all these values are below the x-axis, the same thing is going to happen. All right, I hope that makes sense. All right, that's going to be the out. Now the in is a little easier. Okay, so you want to know the distance from here to here. We know that the distance from here to here is always 3, and we know the distance from here to here is going to be the height of the line. The line is x minus 1. So our distance is 3, and then we want to take away this much. All right, if we take 3 and we subtract this much, then we'll get this distance. So this, I'm almost off my graph, or almost off the video here. This will be 3, and then we take away the x minus 1. Let me make sure that came out on the video. Yeah, okay. So this is the in. A little tricky. All right, I've got my out, I've got my in. Now let me go back and determine what that point was, because I need to figure out where I'm going to integrate from. I know it starts at 1, just from my picture, because it was pretty good. But I don't know where it stops. So I have to set these two things equal to each other. So I need to set x minus 1 equal to x squared minus 4x plus 3. And then I just move things over. 0 equals x squared minus 5x plus 4. That gives me x minus 4 times x minus 1, which gives me two solutions, 4 and 1. Now I already knew 1 because I had it right here. Now I know that this was 4 over here. All right, so with that I can set up my integral. Got everything I need. The volume of this solid of revolution will be pi integral 1 to 4, and then the outer squared minus the inner squared dx. Now this outer, I didn't do this, I didn't clean it up over here. I'm going to clean it before I go in there. I'm going to distribute the negative through, and you would get 3 minus x squared plus 4x minus 9. And you can combine the 3's together. And if you do 3, take away 9, you get negative 6. So that'll be negative x squared plus 4x minus 6. And then the other one, if you distribute the negative through, you get 3 minus x plus 1. 3 plus 1 is 4, so that's 4 minus x. And that's it. Now, you would have to actually expand this out, FOIL it, and I mean, it would be this times itself, and then here, same thing, and then you're off, you're in business. All right, that one was a little complicated, especially this piece right here. Especially this. Got to think through this a little bit. Your instinct is to just want to take 3 and add this much. It's the fact that it's underneath the x-axis tells you need to subtract it, so that the double negative will turn into the plus you need in order to make the distance greater than 3 as opposed to less than 3. All right. $17. All right, I was waiting for one of these. Y equals x cubed. Y equals root x. We're rotating this about x equals 1. All right, so y equals x cubed. Let me start with the square root of x. That's a little easier to draw. Square root of x starts here. At 1, it's at 1. And then we'll go out 2, 3, 4. At 4, it's at 2. So we got a graph that looks like this. Probably won't need that much graph, but that's what I've got. Okay, and then on the next one, x cubed. At 0, I'm at 0. At 1, I'm at 1. At 2, I'm at 8. And in here, it's going to go like this. On the other side, it does something like that. So I can see my region. This is my region. And we want to rotate it around the line x equals 1. Now, x equals 1 is a vertical line, not a horizontal line. So I want to rotate it around this axis right here. Okay, so I look at this picture, I realize, you know what? I drew it a little too small. I'm going to start over just to give myself some more room to work with here. So I'm going to erase this. We come back in here. focus a lot of my attention here in that first quadrant, like this. And then I know with the blue one, the square root of x went like this. Let's say that that's 1 right there. And then with the green one, it went like this. Of course, it keeps going, and the blue one keeps going. So this was root x, and the other one was x cubed. But we're trying to rotate this around this line, which was x is 1. And my region here is there. So, now, there is a technique I can use called the method of shells, which I will talk about in class, but let's try and do this one with the method of washers and discs. So I cannot use a vertical rectangle here. As much as I want to, I can't, because with method of discs and washers, your rectangle has to be perpendicular to your axis of rotation. So here's my axis of rotation, here's my rectangle. They're parallel, not perpendicular. So I have to use a rectangle that goes sideways. Now if I do this, okay, if I use a sideways rectangle, then these functions, the blue one and the green one, have to be functions of y, not functions of x. Right now they're functions of x. So what I need to do is convert these. I need to solve these for x. So I'm going to take the cube root of y, or cube root on both sides, and you get this. And then here I'm going to square both sides and get that. So now you have x in terms of y, x in terms of y. These are both functions of y. So I'm going to come back in here, and the blue one is actually going to be y squared. And the green one is actually cube root of y. And that way I can actually draw this out with the sideways rectangle. All right, so now how do we transpose this? Kind of can go up or down with it. I'm going to go up. Just remember that's our axis of rotation there. It's a little easier for me to draw above this. So I'm going to draw, first of all, my y-axis here. Here's my rectangle. I have the blue function on the left, the green function on the right. My axis of rotation is here. And so I need to get an outer radius and an inner radius. So I stand on the axis of rotation. I look out to the farthest edge of my rectangle, which is right here. I have to figure out that distance. Then I have to figure out the distance from here to here. Well, we know that the distance from here to here, from the y-axis to here, to the blue, is the function of y. So I know that from here to here is y squared. I also know that the distance all the way from here to here has to be 1. So if the distance from here to here is 1, I'm probably off my video, but I think you heard what I said, then this distance here should be that total distance 1, taking away the y squared. So like if this was 1/2, or not 1/2, if this was like 1/8, then this rest of it would be 7/8, and that you get that by doing 1 minus an eighth. Same exact principle for this one. You know that the distance from here to here is cube root of y, that's this distance, y-axis to here, and that means that this distance has to be the 1, take away the cube root of y. Now this one is the inner function, this one is the outer function. And again, that's because if we're standing on the axis of rotation, the furthest one away, that's the outer one, the closest one is the inner one. Now we also need to determine our limits of integration, and since we're doing a horizontal rectangle, we're going to be differentiating with respect to y, so I need my limits on y. This region starts at y equals 0 and stops at y equals 1. And that should be it. I should be able to set this thing up. Okay, so the volume of this will be equal to pi integral 0 to 1 outer function squared minus inner function squared dy this time, not dx. And then what is the outer function? It's 1 minus y squared. The inner function is 1 minus the cube root of y, and then dy. So you'd have to square this. That's expanding that out. You have to square that. That might be a little weird. 1 minus, I'm going to rewrite that as y to the 1/3 squared, which means times itself. And then when you multiply that out, you get 1 minus 2y to the 1/3. So 1 times 1, then 1 times this is itself. 1 times this is itself. There's negative 2 of them. Then this one times this one is positive y to the 2/3 because you add the exponents. 1/3 plus 1/3 is 2/3. So that's what this would be. You'd have to distribute the negative sign through, then do all that. And then you'd have a bunch of powers of y and you integrate using the power rule. No big deal. All right, that was interesting. All right, so the next ones are calculator problems. I'm just going to say let's just set these up. All right, number 19, let's just set it up. Okay, y equals e to the negative x squared, y equals 0, x equals negative 1, x equals 1, and part A says about the x-axis. That's part A. Part B says about y equals negative 1. So let's try this. Again, we've got to graph it. Let's take care of the easy ones first. Y is 0 is the x-axis. X is negative 1, vertical line. X is 1, vertical line. And then finally, what color have I not used here? I have this other one, it's not very good though. I'll try it. Y equals e to the negative x squared. So let's just plug in some points. If x is 0, you get e to the 0, which is 1. So I know at 0 I'm at 1. And then if I plug in, let's say negative 1. Let's just see where I am here. I plug in negative 1. Negative 1 squared is 1. Negative 1. So you get e to the negative 1. E to the negative 1 is 1 over e, which is going to be a small number, which is going to be like this. And then if I do positive 1, the same thing happens. I square it, I take negative, it gets the same result, so it's like this. And then as I go out further, they're going to get smaller, so it's going to look something like this. Okay. So now, the region we're talking about is the region bounded by all of those, which is in here. And I want to rotate for part A around the x-axis. So the x-axis is here. I'm going to do a vertical rectangle. I'm going to transpose that over here. Here's my axis of rotation. My rectangle's here. My top function is that e function. The bottom function is going to be the red y equals 0. So the outer radius is the distance from here to here. It's e to the negative x squared. And then the inner radius is 0 because it's not moving. And my limits of integration are -1 to 1. So the computer, the book asks you to do this and use a computer to integrate it. So you can go to Wolfram Alpha, see if you can figure it out. But really, it's just the setup is what I wanted you to do here. So the volume will be equal to pi integral -1 to 1 of the outer squared. So e to the -x squared squared minus the inner, which was 0 squared, dx. So when you actually do that e to the -x squared, be careful, because what you do here is you multiply these two powers. So -x squared times 2 gives you -2x squared dx. And we do not have a way of integrating that easily. Okay, so we are in trouble if we try and integrate that by hand. But that's why in the book it says use a computer. All right, so that's part A. Part B says we want to rotate around y equals -1. So let me show you how that's going to change it. The picture's still exactly the same, except now we're going around a different line. So we're going around y equals -1, which is a horizontal line like this. That's our axis of rotation. So when I come over here, draw my x-axis, draw my rectangle, have my curve on top, curve on bottom. Now, if I'm standing on my axis of rotation, which is here, I'm looking out. The outer edge, the outer radius is this, the inner one is this. So the distance here should be pretty easy to get. We know the distance from the x-axis to I don't know, I guess that's a greenish, bluish color, I don't know. This one, that's e to the -x squared. And then I just need to add this much distance, which is 1. So this will be 1 plus e to the -x squared. And that is my outer. My inner radius is from here to here. The red one never changes. It's always the same function. So it's just this distance, which is 1. That's my inner. And the limits of integration don't change. So all that's going to change is what's in this integrand. The outer is 1 plus e to the -x squared minus the inner this time is 1 squared dx. And we would actually have to FOIL that out, but see, we can't integrate this anyway. We have to use a computer to integrate it, so that would be the setup. All right, I like that. I'm just looking here. All right, I had one in mind. It's not in the book. I was thinking about one that was pretty good. Let's say you have y equals x squared sine x. You've got y equals 0. You've got x equals 0. And x equals pi. And we want to rotate this about the x-axis. You know what? Hold on. Let me see if I want that. How about x sine x? That's still going to be kind of a problem. Well, I don't want to work through this one, actually. I want you to think about this one. I don't want to do it. Well, let's just go instead from there to there. Let's go to go to 1. So I'll help at least set it up, the picture. If x is 0, I'm going to graph the top one. If x is 0, you get this. If x is 1, you have e. And then whatever it looks like in there, you could plug in some numbers, but it's going to connect like that. And so you're looking at a region right in here. What would be interesting about that problem is it's a pretty easy setup, but I would challenge you to try and integrate it. It's a pretty interesting integral to try and do by hand. All right, I won't say any more about that. All right, so I think I have enough time to do one of these weird problems where you have a base that, well, let me just do it. I'm sure I'm going to do one of these in class. Let me look at number 38. Says the base of a solid S is a circular disk. Parallel cross sections, that's the end of that sentence. Parallel cross sections perpendicular to the base are squares. And the instructions here are to find the volume. Find the volume. Of the solid. Do you have a minute? Do you have time? Do you have like 5 minutes? I'm going to finish this up.
Fine.
Okay. Which cal are you in?
2.
2? All right. You can come in then. I'm doing a cal 2 problem, actually. All right, so in this problem, they don't give you the actual circle. So if I'm looking from the top down, I have a solid whose base looks like a circle, like this. They're not telling you what the radius of that circle is or anything like that. So I'm going to change the problem a little bit. I'm just going to make this a circle with a radius 4. And that way it'll be a little easier to work this out. So we have a disk on the ground. This is the bottom of this solid. The perpendicular cross sections. So imagine there's some solid above this, and if I come through and I take a slice out of that solid and look at it from the side, it needs to form squares. So here's where we try and get an idea of what this looks like in three-dimensional space. So imagine again, you've got your circle, which is on the ground, which looks like this. That's your circle that's on the ground. And then this is our x-axis, this is our y-axis, so that's laying flat on the ground. If we come through and we take a cross-section of this solid, let me do it in a different color. We take a cross-section that's parallel, so we're running a line parallel to the y-axis, so it's like this, that red line. If we look at that, and we look at that where it's sliced into the solid, it will form a square. That means all sides are the same length. And so what happens is if I take another slice, like a slice that's a little bit closer, like over here, then it'll look like this over here. And notice that that length is not as big as the red one, so the square above it would not be as big. And if I got really, really close, like that, then that square is going to be really, really small, like that. And so if we connect all these together, imagine all the different cross sections together, you're basically going to be connecting their edges together like this. And then they would go back down to 0, and then it would do the same thing on the other side. You go back down to 0. And you've got this weird looking shape. Do my best here to try and draw it. And that's it. That's three-dimensional. It's kind of hard to see. On the back side it curves around, but that's some weird shaped solid that if you take slices and open it up, each slice looks like a square from the side. So the question is, what's the volume of this? So what we're going to do is what we've done before. We're going to take one of these arbitrary slices, and we're going to imagine that slice laying on the ground. Draw my little picture again. That slice laying on the ground looks like this. And then when I come up and make a square out of it, looks like this. So moving all that stuff over here, we've got this picture. Okay, so I want to know what the volume of that little piece is. So if I know this side, and then this, I can find the volume. Well, this side is easy because that's just the width of the rectangle, which is dx. That's always been dx. And then from here to here has to do with the circle itself. It's this distance. It's not the radius, because it changes as I go. So I need to figure out the distance from here to here. Well, to do that, I need to know the equation of the circle. And since the radius is 4, I know the equation is x squared plus y squared equals, 16. And so what I'm going to do now is I'm going to solve this for y, move the x squared over, take the square root, and only look at the positive one. So I know that this top curve right here, that right there actually goes this way too, right there. That the distance from here to here is that. That's the y value right there. So the distance from there all the way down, because of symmetry, is double this. So I know that this length right here will be twice as much as this, 2 square root of 16 minus x squared. And if that's what this side is, this side has to be the same thing because it's a square. And so the volume is this times this times this. So the volume of that little sliver is 4, and then the roots multiply, and the roots are gone, so 16 minus x squared, and then dx. You could distribute the 4, but that's not important. So that's the volume of one of the slices. And you want to take all of them up and add them up forever. So you bring in the integral. So the volume of the entire solid will be the integral. Notice I don't need a pi out here because I'm not doing, this is not a solid of revolution problem. This is totally different. I just need my formula. So it's the 4, it's the 16 minus x squared dx. I'm going to add up an infinite number of them, and I'm going to let my x values vary between -4 and 4, because that's how I'm going to move that rectangle back and forth. So -4 to 4. Whatever that is, that's the volume of that solid. All right. Okay, this homework set that I'm going to do here is actually for my internet class, but it will help any of my Cal 2 students. So working out of the homework for the internet class, I'm going to start with, this is for section 7.2, number 2. So it says to find the volume of a pyramid whose base is a square. So you have a pyramid, the base is a square. the side of which is L, so L all the way around. It's a pyramid, and they're telling you the height, you know, from the center up is h. So it's to find the volume of this. All right, so what we're going to do is we're going to imagine laying this pyramid sideways. Okay, so it looks like this. All right, just looking at it straight from the side. We know, and I'm going to orient it onto the xy axes like this. We know that the distance from here to here is L. We know that the distance from here to this point is h. So that's the point h right there on the x-axis. And let me make sure my video is recording here. Okay, it looks good. All right, so imagine now that we're going to take a bunch of slices. So a bunch of infinite slices of this. If I take one of those slices and look at it, it's a cross section of this pyramid, it's kind of like taking a slice out of here. And I'm going to find the volume of that little slice. So imagine a little sliver of the pyramid. So to do that, I have to take a slice from in here, and I have to determine over here in this picture what the volume of that slice would be. And then I'll add up all those slices, and I'll go from 0 over to h. So we know that this side, whatever it is, I don't know, I'll just call it s, is equal to this side s. And we know that this is dx. That's the width of the little sliver. So if we can just figure out what this side is, we know we can find the volume. But that side is not L. L is only the very end. So we need to figure out, you know, this distance. So to do that, I'm going to use the fact that I know a little bit about this line right here. This point right here has the coordinates h, and then if the whole distance from here to here is L, then halfway will be L over 2. And I have another point, which is this one, and that's the point 0, 0. And so the equation of this line can be obtained by using the formula y minus y1 equals m times x minus x1. The slope of this line is y2 minus y1 over x2 minus x1. So it's y2 minus y1, which is 0, over x2, which is h, minus 0. So this is L over 2 over h, which is the same as L over 2h. That's the height, that's the slope of this line. So it's L over 2h. And then I just need to use one of the points and plug in here, and I'll just use 0, 0 because it's easy. X minus 0 over here, y minus 0. So the equation of this line is y equals L over 2h x. So that means that the height from here to here is going to be L over 2hx. It's the y coordinate of this point right there. And since I want to know this entire length, it's going to be the same thing, right? L over 2hx. Double that, right? So if I double this, take 2 of those L over 2hx's, multiply by 2, I just get L over hx. So this side s is actually L over hx, and this side's the same thing, L over hx. And so the volume of this little sliver is this times this times this. So dx is at the end. When you do this, you basically square it, so you get L squared over h squared x squared. And so what I want to do is I want to add these up. I want to add them up forever, or an infinite number of them, and I want to move my sliver from 0 to h. So kind of should have pointed this out earlier. This is not a solid of revolution problem. This is something different. So the volume of the pyramid should be the integral from 0 to h of L squared over H squared X squared dx. And L squared or L and H are constants in the problem. That's the pyramid that's already given to us. So I can pull the constants out of the integral, and I can just integrate the x squared. So this becomes L squared over H squared times the antiderivative of x squared, which is 1/3 x cubed, evaluating from 0 to h. So now what I do is I replace my x with h, so I get h cubed, so L squared over H squared times 1/3 times H cubed minus, now plug in 0, everything goes away, you get 0. And then we clean this up. I can cancel out 2 factors of H, that makes that just an H, and that gives me my final result, which would be 1/3 L squared H. All right. Okay, the next one I want to do is number 8. So it says find the volume of the solid rotating the region bounded by y squared, it's number 8, y squared equals 2x, x equals 2y, about the y-axis. So this is a solid of revolution problem. I need to draw out these curves. So I need to determine if I'm going to look at these as functions of x or y. But I'm going to be rotating around the y-axis, which means that my rectangles are going to need to be sideways, horizontal. So I'm going to be needing to solve these for x. So solve that for x, you get x is going to be 1/2 y squared, just dividing both sides by 2. This one's already solved for x, so I'm in business. So I need to graph both of those. So let me go ahead and do that now. Let's graph this one because it's a line. If y is 0, x is 0. If y is 1, x is 2. And it's a line, so I can just draw. Okay, that's x equals 2y. Now to draw this one, if I let y be 0, I get x is 0. If I let y be, let's be clever here. Well, let me do 1. If y is 1, then x is 1/2. Let's see, remember this was 2. So here's 1, it'll be here. If y is, I'm going to try and pick a nice one here, 4. 1, 2, 3, 4. If y is 4, sorry, I meant to say 2. If y is 2, 2 squared is 4, 4 divided by 2 is 2. So if y is 2, x is also 2. And then if y, should I do another one? If y is 4, should we do that? 4 squared 16 is 8, so if y is 4, it's 8, it's way over here. So we've got this parabola going like this. And somewhere it looks like they're going to hit each other. Somewhere, I don't know where. And so I've got my region in here. And I'm trying to rotate that around the y-axis. So my rectangles are going to need to be sideways like this. And so I need to know to integrate from, what y value, from 0 up to where? Wherever these hit. And I'll have to figure that out later. But let's just set up the actual outside radius and inside radius first. So I'm going to transpose this down. Here's my axis of rotation. I bring the rectangle down. And then I have my red one is going to be on the right. My blue one is on the left. And so I stand at the axis of rotation. I look out and I look for the outer radius, which is from here to here, which is the red function, which is actually 2y, because remember it's a function of y. And then the inner radius is from here to here, That's the blue function, which is 1/2 y squared. So this is my outer one, and this one right here is my inner one. So I'm almost ready to set up the integral, except for the fact I need to figure out what this limit is. So I have to set these two equal to each other. So I'll do that now. I'm going to set 1/2 y squared equal to 2y. When I do that, I'm going to multiply both sides by 2. Y squared is 4y. Subtract 4y on both sides. I factor a y. And I set equal to 0. I get two answers, 0 and 4. So up here at 4, this is where they hit each other at 4. That y value is going to be where I stop my integration. Of course, it started at 0 and then went to 4. All right, so now set up the integral. This is going to be, the volume is equal to pi, integral 0 to 4, outer function squared minus inner function squared dy, because our rectangle is horizontal. So the outer one is 2y, and the inner one is 1/2 y squared. And then you square them and you go through all the integration, which I'm not going to do. All right, hope that helped. All right, the next one I want to look at is number 9. So for number 9, give you y equals 2e to the negative x, y is 2, x is 2, and you want to rotate this about y equals 4. So I'm going to start with my graph of my region. All right, let me start out with let's take care of the easy ones first. Y is 2 is a horizontal line through 2. X is 2, the vertical line through 2. And then y equals 2e to the negative x. So let's plug in 0. If we plug in 0, we get e to the 0, which is 1. 2 times 1 is 2, so it's right there. And if I plug in a number like 2, e to the negative 2 is a really small number, times 2, it's small, so it's going to be like this. And then it's an exponential that's been reflected, so I kind of already knew that, but this is the graph right there. So the region that we're talking about is this region right here. We want to take that and we want to rotate it around the line y equals 4, which is up here. I'm going to rotate it around that. So my rectangle that I'm going to use is going to be in here. It's going to be vertical, and I'm going to wrap it around like that. So come over here and I draw axis of rotation. My x-axis is down here. And what do I have there? Red, green. So my green one's on the bottom, red one's on top, green one is on the bottom. This. So I need to find my outer radius and my inner radius. So I'm standing on the axis of rotation, which is up here. I'm looking out, trying to find the outer radius, which is that, and the inner radius, which is this. Now, because the x-axis is here, I know that the distance from here to here is the 2e to the negative x. I know the distance the entire way is 4. So the distance from here to here will be the 4 take away the 2. So this will be 4 take away the 2e to the negative x. Same exact story here. the distance from here to here is 2. That's always the same, right? Because the red stays the same the whole time. And if the whole distance is 4, then that forces this to be 2. Never changes. So we have the outer one here. We have the inner one here. Now our limits of integration go from 0 to 2. And so we can go right to the integral. So volume is pi integral 0 to 2 of the outer function, which is 4 minus 2e to the negative x squared minus the inner function, which is 2 squared dx. And you have to square this, so you have to FOIL it, and it should all work out. The integral on that's not too bad. You're just integrating e to the negative x. We've done that before. All right. What else? Okay, number 11. Y equals 3 sine x. Y equals 3 cosine x. 0 less than x, less than or equal to x, less than or equal to pi over 4. You want to rotate this about y equals negative 1. So let's start with a picture. All right. So when we look at 3 sine x, that's a sine curve with an amplitude of 3. So we know that sine, if we go out to 2 pi, sine should go like this. Up, down, back up like that. Now we are only looking between 0 and pi over 4, which is right here. That's pi over 4. So my graph, I really don't need this whole thing. So I just wanted to point out this is what sine looks like, and our amplitude is 3, so we know that that's 3. So what I'm going to do is I'm just going to kind of blow this graph up a little bit, just to make it a little bit easier to look at. Here's pi over 4. And let's say this is 3 up here. And we knew that sine started here, that it went up and hit its peak right there. Okay, right at the pi over 4. Now cosine, 3 cosine is, remember if you graph cosine, cosine looks like this to 2 pi. So we're only going to be looking at, let's see, cosine of pi over 4, we're going to be looking right in here. Oh shoot, you know what? Hold on, it's pi over 4, not pi over 2. All right, this is not correct. This is pi over 2, I apologize. This is pi over 2. So pi over 4 is in here. I don't know why I did that. So this is the correct sign, but it goes to the top at pi over 2, not pi over 4. I don't know why I did that. All right, so cosine, 3 cosine of x, would start up here, and at pi over 2 it would be 0, so it looks like this. Okay, so this is pi over 2. Pi over 4 is in here. So somewhere in there they hit each other like that. And we're trying to find the region bounded by these. We're told that the x value has to be between 0 and pi over 4. So here's 0, here's pi over 4. So we're looking at this region in here. Right there. And we want to rotate that about the line y is negative 1. So y is negative 1. It's down here. That's our axis of rotation. So I'm going to use vertical rectangles like this. Take those and wrap it way around this line down here. So I'm going to transpose that over here. Here's my rectangle. Here's my x-axis. Here's my axis of rotation. I have the blue function on top, which is the cosine curve. I have the red one on the bottom, which is the sine curve. I'm going to stand on the axis of rotation, look out to the far edge of my rectangle, which is way the heck out here. Find that, and then I'm going to find this one. So we know that the distance from the x-axis to the blue, that's 3 cosine x. But then we need to add this distance. And this distance from here to here is always going to be that distance, which is 1. So I'm going to take 1 and I'm going to add to it the blue one, which was 3 cosine x. So the total distance is 1 plus 3 cosine x. Same thing with this one. From here to here is 1. From here to here is 3 sine x. So this distance all the way from here to here is 1 plus 3 sine x. So this one is my outer. This one is my inner. My limits of integration go from 0 to pi over 4. So we've got volume is pi integral 0 to pi over 4. Outer function 1 plus 3 cosine x squared minus inner function 1 plus 3 sine x squared dx. And then you would FOIL these out, and you're going to have some sine squareds in there, some cosine squareds in there. You're going to have to use the half angle identity. That's a tough integral. Not tough, it's just a long integral. But I've got it at least set up for you. Let's see what else. Number 12. Number 12 says that we have, it says find the volume of the solid described here. The base of S is the region enclosed by y equals 5 minus 3x squared and the x-axis. So I've got a region that's created from those two things. It says cross sections perpendicular to the y-axis are squares. We're supposed to find the volume of this solid. So let's try and draw a picture. First of all, let's look at the base. All right, if we call this x and y, we need to graph this thing. So we've got the x-axis here, which is creating one of our bounds. We've got this parabola. This parabola is a parabola that opens down because I have a negative 3 and has been moved up 5 because I have plus 5. So up here at 5, it starts and then it comes down like this. Down. So the region that we're talking about is this region in here like that. And it says now that the cross sections of this solid perpendicular to the y-axis. So if I come in here and I take a cross section that's perpendicular to the y-axis, I'm talking about a cross section that's like this. Imagine a little infinitesimal cross section of that. When I look at that cross section in three-dimensional space, it's a square. So let me try and draw three-dimensionally to help you see this. This is x, this is y. So our parabola is on the ground here. Here's 5 up here. And the parabola comes down like this. Like that. Crosses through our x-axis. We have our blue x-axis here. So that's like this sheet laying down on the ground. Our region is in there on the ground, right? And when I take this cross section, that cross section comes across like this, has a little thickness to it, goes up, creates a square. Go straight up, over, and down. Has a little thickness to it like that. So that is that's what a cross section looks like. And if I get a cross section that's a little bit higher up, like here, then in the back, it's behind this one, is going to be a smaller little square. And of course, this cross section down here would be really big. So what I'm trying to do is find this volume of that. So what I'll have to do to find the volume is I'll have to figure out what the formula is for the volume of one of those slivers. And it needs to be in general, and then I'll have to integrate, add them up forever. So let's take a look at one of those slivers. So let's talk about, we know it's a square, so whatever this is, that is. Do we know how thick it is? Well, that thickness comes from this thickness, and it looks like since my rectangle is horizontal, I'm going to have to be integrating with respect to y. So I know that this thing is dy. So how wide is it though? Well, I have to come back over here and I have to figure out the distance from here to here. Well, there's a problem with that because right now this is a function of x, so I can tell you what the height is, but I can't tell you this. So what we'll do is we'll take this and we'll solve it for x first. So let me move the 5 to the other side, trying to turn this into a function of x. I'm going to swap sides on the equation, like that. Divide by 3. Take the square root. Like that. Now I should do plus or minus. The positive one will give me this one, the minus would give me this one. So I'm going to say that this distance from here to here is root 5 minus y over 3. That's the x value. If somebody gives me the y value, that's the x value. And now that represents just this distance. By symmetry, the other side is double that. So I just double this. So that means this side right here is 2 of the root 5 minus y over 3's. But if that side's that, then this side's the same thing. And so the volume of this will be this times this times this. So the volume of that sliver is 2 times 2, which is 4. The root times the root goes away. And then dy. That's the volume of one sliver. And I want to add them up forever, or add up an infinite number of them. So if I add up an infinite number of them, I'm going to need to know where to integrate from. So as I move that rectangle, the rectangle moves up and down, so the y-coordinate is changing. And it's pretty obvious that the y-coordinate is going to start at 0 and stop at 5. So the volume of this will be the integral, not pi, because it's not a surface of, a solid of revolution, 0 to 5, and then this formula, I'm going to clean that formula up a little bit, pull that 3 out, pull the 3 out in front. That formula, dy. So that's it. That, whatever that is, you can figure out what that integral is on your own. Let me make sure I covered that properly. Go. Okay, last one that I'm going to do is number 15. Y equals 5x, y equals 5 root x. and we're rotating this about y equals 5. I'm going to go quickly through this. Y equals 5x looks like this. Y equals 5 root x looks like this. They hit each other at 1. Check it for yourself, plug 1 in, you get 5 on both of them. And so the region that you want to integrate is this one. You're rotating around y equals 5, which is up here, right there. And so your rectangle is vertical like this. Here's your rectangle. Here's your axis of rotation. This distance is the 5, and take away the bottom function, which is 5 minus 5x. This one, that's terrible. This one, the inner radius, is the 5, but then take away this curve, which is the 5 root x. So this is your out, this is your in, and then you set up the formula, integral pi. We're going to integrate from 0 to 1, the out squared minus the in squared, and I'll let you finish it up. Out squared, in squared. All right, I hope that helps out a little bit on that 7.2.